Hi, it's Mrs. Lemke. We're here today to learn together about some trigonometric identities. And so before we get rolling with the trig part, let's focus on that word identity. An identity is something that is true for all values. So for instance, x plus 0 equals x is a true statement no matter what I put in place of the x. 1 times x equals x. Also an identity. It doesn't matter what is true, what value x takes. This is in contrast to what we would call a conditional equation. A conditional equation is only true on the condition that this x represents some particular value, in this case 3. So x plus 2 equals 5 is only true on the condition that x equals 3, whereas an identity is always true. So some identities that we already know in the world of trigonometry, well, one that comes to my mind is the fact that cosecant and sine are reciprocals of each other, which I could express this way. I could also express it by saying sine is 1 over cosecant. Another identity that we might know, there's so many, would be that sine divided by cosine gives me tangent. Another identity that we might know would be from our unit circle understanding of things. And say, all right, we're looking at our reference triangle here. And I know that this side is the x or the cosine. And I know that this side is the y or the sine. So that this ordered pair is cosine comma sine. And since I am in the unit circle, the radius is 1 unit, which means that x squared plus y squared equals 1 squared, or cosine squared plus sine squared is 1. That's called the Pythagorean identity, in case you didn't know that, okay? And there are other Pythagorean identities that you can get by dividing through. If I take that sentence and divide through by cosine squared, I'd get another Pythagorean identity. If I take that sentence and divide through by sine squared, I'd get another identity. So how many identities are there? Infinitely many. Do you like when I write half English and half math? I do it all the time. I really should incorporate more of that into the class. All right, so here is a statement. We're not sure if it's a conditional equation or an identity, so we're going to kind of explore that. And so we say, all right, well, let's check and see if this works. All right, I'm going to try an angle. I'm going to try pi over 6. Pi over 6 is one of my favorite angles. What's your favorite angle? Have you thought about that at all? Okay, and so I'm not going to say that this is equals. I'm going to invent the notation of equals question mark. So I shouldn't assume that it's equal. I'm trying to find out if it's equal. I think equals question mark should have its own name. All right, so here we are, and we have to think about, pi over 6 in the unit circle. We get to think about pi over 6 in the unit circle. We have to think about that ordered pair and say, okay, let's plug in some values. So we have 1, and cosine there is root 3 over 2, and sine is a half. And I don't know if that's equal to, no, now I've got to think about cosecant reciprocal of sine, and cotangent reciprocal of tangent, also cosine over sine. So root 3, oh my gosh, this is a lot. And then I have to think over here, dividing by a half is the same as multiplying by 2. And then I would distribute, and then 2 plus root 3. Oh, that is equal to 2 plus root 3. Okay, so this one checked. And I'm thrilled, except also distraught. Because look, I also have to check this. I also have to check this. If I want to know if this is true for every angle, that's going to be my life's work, and I still wouldn't be done at the end of my life because there's infinitely many angles. That sounds really, really, I'm deflated. So I think it's algebra to the rescue, my friends, because, there's just no way to check every single angle. It's impossible. So we could spend all day checking not just all day, we could spend forever checking to see if it works for every single angle. Instead, we're going to use the generalizability of algebra to our power, okay? So what you do here, it's very important that you do not manipulate both sides of the equation. That would be assuming equality. Remember that whole equal sign question mark thing? Okay, so we should not assume equality. If we do things to both sides of the equation, that's assuming our hopeful conclusion that things are indeed equal. So we pick a side to work with, and I'm going to choose the left-hand side. Now, I actually like to write down which side I'm working with, left-hand side, right-hand side, and make that very clear to the reader of my paper, which right now is you. All right, and then I'm going to show that I am splitting this up. Now that is something I can do because that's how fractions work, my friends. If you are adding, oh, sorry, thinking ahead of what is going to happen next, sorry about that. If I'm adding fractions together that have the same denominator, I add the tops, I keep the bottoms. That's the way we usually think of using this property. I'm just using it backwards. I'm taking something like this and splitting it up, okay? So this is 1 over sine plus cosine over sine. And I show that underneath my first step. And then I'm going to think here and say, all right, I'm going to keep an eye on the prize. I'm trying to see if I can get it to look like that. I think I can. Because 1 over sine, the reciprocal of sine is cosecant. So that's what that means. When we say they're reciprocals, it's like 1 over one of them is the other one. That's what we mean, okay? And then cosine over sine, that is cotangent. That's one of the things that I know. All right, now if you didn't know that, that would be a little harder to deal with, right? You might do some other steps in case if you didn't know that cosine over sine is cotangent, then you might have to do some other things to kind of manipulate that, right? But I did know that, so I got all the way to the end. So now this is the right-hand side. And if you connect the left side and the right-hand side, you have actually done a proof, which is just fantastic. People do different things at the ends of proofs. Sometimes a happy dance, sometimes draw a smiley face. We'll talk about some other options as we go here. Okay, so question 2, or example 2, says prove the following identity. Well, this one's a little bit harder to decide, maybe, like which side to start on. Generally speaking, having an addition or a subtraction sign is a little bit more complex. And generally speaking, you actually want to start on the side that's more complex, because our algebra lives have been focused on simplifying, not complicating. So we have a lot more skills with making something that is yuckier into something that looks nicer. So try to pick the yuckier looking side. Plus and minus are a little bit yuckier than multiplication, in my experience. Okay, so here we are with tangent and cotangent. I know somehow this addition has to go away. I'm not really fully sure how that's going to happen, but we'll just kind of, sometimes you don't know the whole thing, right? You don't necessarily know, oh, this is the 4 steps I have to write. Sometimes you just have to put your pencil in motion and say, all right, what is it that I know about tangent? Tangent, I know, is sine over cosine. That is something I know. And even if you didn't know that thing from the last question, you learned it, right? That cotangent is cosine over sine. That does make sense, right? Because tangent and cotangent are reciprocals. And so if tangent is this, cotangent has to be the flip of it. Oh, that does make sense. I see. Okay. So now I might be in a little bit of like, what is going to happen? But math is math, my friends. You can write that down on your notes. Math is math. That's wisdom from me. Okay. So my point is that if you're adding fractions and they have trig functions in them, That's not really different than adding fractions when you have like numbers or other things, right? So if I am adding fractions and the denominators are different, I need those denominators to be the same. So this first guy, this sine over cosine, if I compare that denominator to this one, my eyeballs are going back and forth between these, that guy needs a sine to match his friend. Oh, I keep doing this where I'm thinking ahead of what I'm going to write next, and it's causing problems. Okay, and then over here, this guy, who's in the problem already, if you look back and forth between those denominators, that guy's missing the cosine. So now, and now if you focus here, one more thing. This part, right, was the part that was in blue. Okay, that box is not serving a mathematical purpose. I'm just pointing it out. This is equal to 1, and this is equal to 1. So that's why it's legal to do, right? You're just multiplying by a very strange version of 1. You're giving the parts of the equation a little makeover. They're going to look different, but they're still going to be the same. All right, so bottom, this denominator is sine times cosine. This denominator is sine times cosine. So I can now add those fractions together. And when I add fractions together that have the same denominator, we talked about this back here, when I have the same denominator, I just add across the top, keep the bottom. So that's what I'm doing here. I'm going to add across the top, so I have sine times sine, sine squared, plus cosine times cosine, cosine squared. That's a thing, right? Back here, cosine squared plus sine squared equals 1. That equals 1. You know what else is really good about that? We got rid of the plus. Look at us. Okay, time to do a little quick check-in about where we're supposed to be here. The other side of this looks like secant times cosecant. Do I have it? I think I do. Because this that I just wrote is the same as saying 1 over sine times 1 over cosine. Remember, when you're multiplying fractions, you don't need a common denominator. You don't need no stinking common denominator. You're just multiplying. So you just go straight across, straight across. So I just like, those two things that I have on my screen right now are the same. And 1 over sine is cosecant, and 1 over cosine is secant. Is that the right-hand side? Well, I wrote it in a different order, but it's the same. Right-hand side. So some people, when Latin was more of a big thing, I mean, Latin still is a big thing. Don't tell Landvik I said that. So this QED is something that people write at the end of their proofs, right? It stands for, I don't actually know how to say it. Oh, I should have talked to Landvik ahead. Quid erat demonstratum, I think is what it is in Latin. I sometimes write this. Do you know what that means? Piece of cake. I'm not classy like, people who know Latin. All right, so why can't I just verify the identity by checking that it works for a few angles? Because, well, first of all, we already talked about how that would take your whole lifetime, right? I mean, that's not going to work out, but maybe you're thinking don't check all the angles, just check a few. Well, there are things that look true, but they're not. Like if you were to plug in pi over 6 here, that would work. Pi over 3 here, that would work. But then you get to my friend pi over 4, and that does not work. Okay? So the moral of the story is that like underage drinkers, sometimes people have fake IDs. All right? And so we don't want to fall for a fake identity. That would be problematic. Okay? These are actual rules about proving trig identities. You only work on one side of the identity because otherwise you are assuming equality instead of proving it. You cannot assume the conclusion. That's going to break our heart if you do it. Oh my gosh, do not make the math teachers cry. Second rule, do not treat the identity like an equation, right? You can't, well, that is kind of saying this, right? A little bit. Don't say like, oh, I'm going to add something to both sides. That is assuming equality. We can't assume equality here. We are proving equality. So some different advice. Watch for Pythagorean identities or variations on them. Ooh, variations on them. So I know sine squared plus cosine squared of an angle equals 1. So if and I do know that this is true. That's a factual statement. That is factually already an identity that I know is true. So variations on it would also work. So cosine squared is 1 minus sine squared. Or if I have sine squared on one side of the equation, then I'd have 1 minus cosine squared. So that's what we mean by variations, right? Got it. And remember how I said there are other Pythagorean identities, right? If you take the sine squared plus cosine squared equals 1 version and divide through. Interesting. Use algebraic manipulation, right? So things like finding a common denominator. Yeah. Look to use other identities. So if you know like tangent is sine over cosine, you could do that. Convert all trig functions into sines and cosines. That is sort of like the last resort, like the basic if you don't know anything else to do, okay? It does work an awful lot of the time, but sometimes it makes your problem longer. So sometimes there's a more efficient path other than that one, but if you're stuck, that's the guy to go with, okay? There are so many practice problems at the end of this, and I think our video is a little on the long side already, so I'm just going to do a couple, and then I'm going to show you answers, okay, only, and that will, allow you to practice on your own, and then the ones you didn't get, certainly ask about if you're confused, okay? This first guy, kind of a good first example, I'm just saying, because it's kind of basic, okay? All we want to say here is that these two multiply to equal 1. I'm going to start with the left-hand side, because seriously, if I started with the right-hand side, what would I even do? So left-hand side, I'm going to write that left-hand side down. This part, I'm going to replace. I'm going to say secant is 1 over cosine of y, because secant and cosine are reciprocals. And then I'm going to say, all right, I know how to multiply fractions. This will be cosine of y on the top, 1 times cosine. On the bottom, put a 1 here, cosine times 1. Oh, there it is, already. Boom, because that's my right-hand side. Okay, what celebration should we have? Smiley face, QED, POC, piece of cake. Your call. All right, next one. I'm definitely starting with the left-hand side, because that has more to do, and more is better in this case. All right, and I want to think, well, I know something about tangent. And the reason, I won't say that. Don't you wonder now what I was going to say? I think what I was going to say would have been confusing. It's probably good when I edit myself. Okay, so tangent squared is sine squared over cosine squared. Now, if you're like, where did that come from? Tangent itself is sine over cosine. That is an identity that we know already. And so since this is a factual statement, this is a known true statement, I can say this. So tangent squared is sine squared over cosine squared. And you know that we write it like in this weird way with the squares kind of feeling like they're in the wrong place. Seriously, because mathematicians are so freaking lazy that we can't even bother writing the parentheses. I'm just putting it out there. I mean, I support that. I don't like having to write extra. Okay, so sine squared, let's write it as sine squared over 1. And let's write this division as multiplying by the reciprocal. I'm literally just playing around, trying to see. Wait, I think we've got it. Because I'm trying to get cosine squared. Oh my gosh, this is great. Because right here, when I multiply, I know that those would cancel because they make a 1. This is it. These are so fun. I could do these all day. These are fun, is my new way of saying the end of the proof. All right, question 3. Oh, let's just do one more together. Okay, so we'll start again on the left-hand side. Maybe we wrote these all, so you start on the left. That isn't necessarily true. We might have just been in a left mood. Okay, so here we are with this guy, and there's a lot that has to go away to make this into one fraction. So I got to get rid of subtraction. I got to get just down to one trig function. I think I'm going to go with that sine and cosine idea here, because I think there's just so much that has to cancel, and you're more likely to see the canceling if everything's kind of in the same terms, if that makes sense. So the sine, I'm going to write a sine over 1 because everything's in fraction-y form. Okay. Oh, do you see what I see? If I put those together, then I'd have a common denominator. So 1 over cosine minus sine squared over cosine. And because of having a common denominator, I can smush these together because that's how subtraction of fractions works. I just subtract across the top. Do you see it? Do you see it yet? It's so exciting. So, oh, I was trying to pick a different color there. Oh, come on. All right, so cosine, and then 1 minus sine squared is cosine squared. And if I have, like when I have x squared over x, the x over x goes away. So here, one of those cosines cancels the one on the bottom. So like that would cancel one of the cosines. That's the right-hand side. Oh my gosh, this is the most fun thing I've learned all day. I love it. I would very much like for you to try the rest. Number 7, kind of optional because it's a little bit, it's a lot for day 1. You'll get there for sure. But I'm going to pause it. You're going to pause it. Don't cheat. Pause. Try 4, try 5, try 6, then come back and check your answers. Welcome back. So, number 4. I did a little side problem over here in the green colored, okay? So this is my Pythagorean identity, and I just rearranged it a little bit. So I took that Pythagorean identity and I divided every term of it by cosine squared. And then each term gave me a different little trig function to look at. So sine squared over cosine squared is tangent squared. Cosine squared over cosine squared is 1. And this part is secant squared. And then if you move this 1 to the other side by subtracting it, you get secant squared minus 1. Secant squared minus 1 is tangent squared. So that all came from understanding a variation on a Pythagorean identity. All right? We mentioned that earlier as a thing that might come up. And then cotangent squared. You can write it as 1 over tangent squared. And these two guys are reciprocals of each other, or you can say tangent squared over tangent squared, which is 1. And in any case, that is our right-hand side. Yay! This guy. Look at the left-hand side. I took the tangent and made it sine over cosine. And if I am dividing by a fraction, that's the same as multiplying by its reciprocal. And then I wrote my secant squared as 1 over cosine squared. And then there's going to be a cosine that gets canceled, right? The cosine up here can cancel one of these cosines, leaving me with just a single cosine on the bottom, a single sine on the bottom over here, which is secant times cosecant, which is our right-hand side. Now, an interesting thought occurred to me while I was going through that. Your answers Like your pathway in the middle here might be a little different than mine, and that's okay. Don't be erasing all of that. As long as every step is valid, and it'd be really great if you set it up vertically like this, so it's like step 1, step 2, step 3, not like this, step 1, step 2, step 3, step 4. Oh my gosh, that is why I get the gray hair, you guys. Don't set up your paper like that, okay? But you can have variation in your work. Just set it up nicely with the steps nice and vertical, okay? And so this is just a solution. It is not the solution necessarily. Starting with the left-hand side, cosine squared on this one is 1 minus sine squared, variation on Pythagorean, and then just combine like terms here. Bada bing, bada boom, right-hand side. Last one. I told you this one's the challenge one. Here you use something that's called the conjugate. You might remember talking about this in your second year algebra class. I know I talked about it in my second year algebra class that I taught last year. The reason we love the conjugate is because when you have the pattern a minus b, a plus b, that's our difference of squares pattern. Okay, and so I'm making use of that now. So 1 minus sine and 1 plus sine, if I were to multiply that out with all the distributing involved, I get 1 minus sine squared. And that is just tremendously exciting in trig identity life because that is one of those variations on a Pythagorean. Let's leave the top for now. But let's work on this bottom. 1 minus sine squared is the same as cosine squared, right? Because cosine squared plus sine squared equals 1. This is not a way that you should write things. Okay, I was just trying to make it more clear because I'm talking really fast. All right, so now I'm going to look back here and say, okay, what was it I was trying to do? 1 plus sine over cosine. Oh, I think I can get that because look, this cosine would cancel that. And there it is. It just falls out. These are so fun. I mean, I don't know what you usually spend your days doing, you know, if making TikTok videos, cooking with your family, whatever. But this is more fun. You should try it, or at least just as fun. I don't want to dissuade you from cooking with your family. All right, that was it. I hope you learned a lot. Practice these. If you do like, let's say 35 of these, you're going to find it easy. Oh, did 35 sound too much? Okay, do a lot though, okay? Do a lot. See you in class. Or not, the rest of you. I mean, have fun with flying covey. Bye-bye.